Hey everybody, Evan Kirstel here today with Jim Campili of Badu Networks. Jim, how are you?
I'm doing great today, Evan. Thanks.
Well, great to have you here. Super excited to get into our topic around the antidote to over provisioning in the cloud. But before that, perhaps introduce yourself and who is Badu?
Sure. So I've been in the enterprise software business for about 30 years now, and I've been at large public companies like SAP and BEA Systems that was later acquired by Oracle. And I've been at some early stage startups that were also acquired or IPO'd. And I primarily held senior management positions on the consulting services side, as well as product management and marketing sides of those businesses. And I've been CMO at Badu Networks for about 5 years now. And Badu Networks is a company that develops what we and our customers consider to be game-changing network optimization software for WAN, Wi-Fi, mobile, and cloud networks. And the reason it's game-changing is because we designed it intentionally to reflect the changes that we've seen in application and network environments in recent years. So the huge move to the cloud, the proliferation of billions of mobile devices, the rapid adoption of real-time streaming and IoT applications, and basically an environment where corporate IT really doesn't have much control over both network endpoints any longer. And the reason most of the traditional network optimization solutions aren't so effective anymore is because they have not adapted to that environment. So focusing on the topic at hand, over-provisioning is driving massive cloud overspending, and that's really caught a lot of attention at the C-level. Now, Flexera, a company that develops SaaS applications for IT asset management, puts out an annual State of the Cloud report, and it's considered highly credible. Industry analysts refer to it all the time. And in their most recent report for 2023, they surveyed 750 senior IT execs, and what they found was that managing cloud spend was seen as a top concern by 82% of those surveyed, surpassing security for the first time in a decade. So that's a significant change. Now, what they also found is that the average wasted cloud spend was 28%. So basically what that means is these organizations see almost a third of every dollar spent on the cloud is being wasted. That's a huge number. And cloud projects on average come in over budget by about 18%, another significant number.
Wow. I'm not even surprised by these survey results. I mean, I hear it all the time as a huge problem, both on the wireless and wireline side of things.
Yep, exactly. So Flexera basically attributed the results to three main factors. The first was unused or forgotten resources that continue to accrue costs. So this is, for example, VMs that aren't shut down when a project ends. Also, enterprises tend to provision for peak demand, and that means cloud resources are underused most of the time, and that means money is being wasted on them most of the time as well. They also pointed out the ease of upgrading cloud and network server infrastructure whenever you're trying to deal with performance issues in the cloud. And of course, the vendors make it easy for you to do these upgrades because they generate more revenue when you do. But the problem is upgrades typically only work in the short run. So this leads to successive rounds of increasingly costly upgrades, and you end up in kind of an over-provisioning loop. Now, the report missed a fourth factor that's often overlooked, and it's really a leading cause of poor cloud performance, and it drives this budget busting over provisioning. And because upgrades don't deal with this underlying solution, in fact, most of the performance solutions out there don't effectively address it. They only work in the short run. That really is the explanation for it.
Hmm.
And that root cause that these solutions don't deal with is the fact that cloud environments are saturated with packet delay variation. It's more commonly referred to as jitter. And in cloud environments, these random delays come from multiple sources. So VM and container-based applications compete for virtual and physical resources, and that causes random VM scheduling conflicts, hypervisor packet delays, extra hops between virtual and physical subnets, for example, some examples that are pretty common in the cloud.
And doesn't containerization though avoid VM conflicts and those hypervisor packet delay issues?
Well, there's really two parts to the answer to that question. One is that containers are often deployed within VMs. So in those scenarios, the VM scheduling conflicts and hypervisor packet delays are still an issue. And even if they're not deployed inside VMs, they're still competing for virtual and physical resources in the cloud. Now, another thing that's happened recently is we're seeing a lot more applications based on kind of containerized microservices architectures. And what ends up happening is if you have applications that are comprised of these containerized microservices, is even though that architecture is great for reuse and modularity and so forth, the microservices can be spread across multiple servers and even multiple physical locations. And that effectively increases the number of network hops that are required to complete an application's execution. So that contributes to jitter, the random delays and so forth that result from that. Now, of course, what we've seen in recent years is adoption of edge cloud to reduce latency and bandwidth usage by moving the data and the processing closer to the users that need it. And it's kind of a hard requirement for a lot of real-time applications like IoT, content delivery networks, live streaming, virtual reality, and so forth. And these applications are typically deployed at the edge. And because of the nature of them, they tend to transmit data in random bursts. And of course, those random bursts translate into still more jitter.
But virtualization isn't required at the edge, or is it?
No, it isn't. But what we see is a lot of organizations turn to it because it does offer a lot of benefits. Obviously, it's very easy to deploy and scale applications when you use a virtualization approach. So we very frequently see cloud implementations at the edge as well. This last factor is something that the cloud vendors really don't have any control over, but a lot of the last mile Wi-Fi and mobile networks that we all access cloud applications on the client side from are subject to RF interference, fading, and so forth. And this creates random delays that cause jitter. And obviously the cloud vendors really have no control over the wireless network that you're using. And the reality is that jitter on any segment of the network path between the client and server creates jitter on the whole path and impacts network and application performance.
And are there any other factors creating jitter, beyond the kind of random nature of data transmission with these real-time applications?
Well, what you see, for example, with IoT, you have a scenario where the devices are moving around all the time. That changes the transmission path, the length of the path between the device and the receiver. It also create scenarios where you have different payload sizes that changes the amount of processing time required and so forth with each transmission. So there are a lot of issues like that.
Now, what about integration between that edge and the centralized cloud? Doesn't that create additional overhead for edge deployments?
Generally not, because usually what's moved from the edge to the centralized cloud tends to be summarized form of the data. And the data tends to only be transmitted on a kind of a periodic basis. So it's not normally interfering with regular operations at the edge.
I see. Interesting.
Okay, now another factor that's become pretty significant recently is that we're increasingly seeing 5G networks being taken advantage of to support a lot of these real and near real-time applications in the cloud and at the edge. And 5G networks actually compound virtualization because of 5G's architecture. So 5G mostly relies on higher frequencies and millimeter wave technology. Now that's great for transferring high volumes of data with low latency, but 5G signals tend to have much poorer propagation characteristics. It makes them a lot more susceptible to interference and signal degradation or fading effectively. And on a related note, these 5G signals often require a clear line of sight between the path between the transmitter and the receiver. So if you have any obstacles in the way, walls, what have you, signals can get deflected, refracted, and so forth. And you end up having multiple signal paths with different lengths, and that creates random differences in packet delivery times, in other words, jitter. The other thing that comes up with this with 5G is that 5G networks, because they essentially have smaller cells, they use a denser deployment of base stations. And while this helps with capacity and coverage, it also means that devices can switch base stations more frequently. And also because 5G relies on smaller cells and effectively more cells, There's heavy infrastructure requirements involved with 5G versus LTE and some of the previous generations of mobile networks. And that's really pushed mobile network operators to the cloud to keep costs down. So they're basically substituting hardware for software deployed in a cloud environment. But it also means these cloud native 5G networks now are subject to virtualization jitter on top of the jitter that's already generated due to 5G's architectures we were talking about a moment ago on the slide.
Oh, wow. So you're saying there's a kind of negative feedback loop between the cloud native 5G networks and the cloud environments that host them.
That's exactly right.
Hmm. Whoa.
So jitter causes a lot more than random delays, and there's a pretty severe knock-on effect. And it's the TCP, which is the dominant network protocol that we see used in AWS and other clouds, and in fact on networks in general, consistently treats jitter as a sign of congestion. So it has no ability to distinguish between jitter caused by the factors we've been talking about and jitter that is actually due to congestion. So in order to prevent packet loss, because TCP is basically designed to guarantee packet delivery, it responds by slowing traffic until throughput collapses, applications stall, and connections basically drop. And because TCP has no ability to distinguish between jitter that's due to application behavior and other factors, this happens even when the network is unsaturated and there's plenty of bandwidth available. Now, this affects not only TCP, but also UDP and other non-TCP traffic sharing in the network, because obviously, for reasons of cost efficiency and so forth, you don't dedicate separate networks usually to separate protocols. And what ends up happening is a lot of network administrators end up reserving more bandwidth for TCP traffic than they otherwise would because of this throughput collapse behavior in response to jitter. And that means traffic based on other protocols like UDP, another non-TCP traffic, gets starved for bandwidth. So their performance is hindered to some degree. Now, if we think about network functionality in terms of the 7-layer OSI stack that I think just about everybody's probably familiar with, throughput collapse is triggered in the network transport layer. So that's layer 4, and it happens at the transport layer in TCP's congestion control algorithms. And MIT research recently cited TCP's congestion control algorithms as having a huge negative impact and a growing one because of this response to jitter, but they really didn't offer any practical solution. And they came out with this research paper a little less than a year ago. And if anybody watching wants to check it out, they can refer to the link there at the bottom of the slide. And really, there aren't any good performance solutions for this problem. And in fact, some of them even make the situation a lot worse. So, we started out talking about the fact that bandwidth upgrades are often the default solution for performance issues, and the fact that they only work in the short run. And the reason they only work in the short run is because they don't deal with this problem. They don't do anything about the underlying problem of jitter-induced throughput collapse. So what typically happens is, and we've seen this with a lot of our customers before they implemented us, traffic increases to the capacity of the added bandwidth, the added VM capacity when you've done your upgrades. But the incidence of jitter-induced throughput collapse goes up in tandem with that increase in traffic. And this is what leads to these successive rounds of upgrades in this over-provisioning loop and ever-increasing costs that we started talking about in the beginning. Now, another solution that's commonly referred to when jitter is seen as a problem are jitter buffers. Now, these work at the application layer, layer 7, the top layer of network functionality in the OSI model, if you will. And what they effectively do is they reorder packets and realign packet timing, and they do this to adjust for jitter before packets are passed to an application. So packet reordering and realignment can create random delays, and that can ruin performance for a lot of real-time applications, live streaming and so forth. And it actually creates more delays and more jitter, making the problem effectively worse, which is kind of counterintuitive because a lot of network administrators actually do turn to jitter buffers as a solution for jitter.
But they offer some benefit, don't they? I mean, they're used all the time, as you say, to blunt the effects of jitter.
Well, they can offer benefit from a user experience perspective for applications that are not real time necessarily. So that can allow for buffering and so forth.
Yeah.
And as I said, they do improve the user experience, but nevertheless, jitter is still being generated even with those applications because you're still going through this reordering and realignment process. Now, another approach that a lot of network administrators, IT administrators turn to is QoS, or quality of service techniques. And basically, these operate at the network layer and the transport layer also, primarily because they rely on the IP addresses and the port numbers that are managed at those layers to prioritize traffic, control the flow of data, avoid congestion, and so forth. But they don't do anything about TCP's congestion control algorithms, and that in effect can limit their effectiveness as well. Now, obviously, there are TCP optimization solutions that focus on the congestion control algorithms, operate at the transport layer, but they're mainly focused on managing parameters around the size of TCP's congestion window and some of the behaviors around that. So they do things like increasing the size of the congestion window, using selective acknowledgements, adjusting timeouts, and so forth. And what we've seen generally is that the improvements tend to be kind of limited. You can see up to maybe a 10 to 15% improvement in throughput from these techniques. That's something, but it's not much. And the reality is, jitter-induced throughput collapse, if you're going to solve the problem, the only way to really do it is by modifying or replacing TCP's congestion control algorithms. But to scale and be viable in a production environment, you can't be changing the TCP stack or client or server applications. You don't want a rip and replace scenario where you have to change all your network infrastructure, because that just won't work.
Yeah.
So there is a proven and cost-effective solution, and it's our Warp VM solution. So what we've seen and what our customers have seen is that Warp VM improves performance by 2 to 10x or more. And of course, the improvement that our customers will see is going to depend on the amount of traffic, latency, and jitter in their environment, in their cloud and network environments. And we're going to look at the numbers on this, but it's able to do this for a small fraction of the cost of upgrades. So you're getting the equivalent of a major upgrade without paying for it. So we'll talk about that in a moment. I'll walk you through the numbers so you can see, your audience can see in dollars and cents the difference it makes.
Yeah.
Now, it's a single-ended transparent proxy. It deploys as a virtual network function and basically functions as a virtual router. And what it does, among other things, is it replaces TCP's dumb congestion control algorithms, if you will, that can't distinguish between jitter caused by congestion and jitter caused by application behavior, network interference, and so forth, with intelligent ones that can make that distinction. And whenever it detects, and it does this on a real-time basis, whenever it detects the jitter isn't due to congestion, it prevents the throughput collapse behavior. And it does this in real time. It requires no modification to client or server applications or TCP stacks. It's a very clean, transparent proxy. The only modifications that you have to make, and there's no hardware or other software required on-prem or in the cloud, and the only modifications you have to make are to on-prem DNS server entries so that they point to the Warp VM proxy instead of the IP addresses of the VMs or containers that are hosting your target applications. And this is if you want to just focus on the behavior of specific applications, but if you want to target all traffic heading into a cloud environment, so for example, cloud native 5G deployed in a virtual private cloud and so forth, all you have to do is make simple routing changes on the cloud end, and you can target all the traffic going in and out of the cloud. It'll be subject to Warp VM's optimization capabilities. Now, beyond addressing TCP's congestion control algorithms, we've got some other key features in this. We also implement our own flow control in Warp VM, and we're able to accelerate packet transmission by filling unused gaps in bandwidth. So whether it's TCP, UDP, or some other non-TCP traffic, we can accelerate the flow of that network traffic much faster than it would otherwise be the case without us in the network. Now, we have QoS features built in, like allowing TCP and non-TCP packets to be prioritized. And this
Oh,
next
wow. So
point,
Warp VM actually benefits not just TCP traffic?
absolutely, absolutely. So
Oh,
it can benefit all traffic on the network. Now, the other thing, and this is significant, especially in comparison to legacy tools, is that we don't require payload access. So the performance benefits the same for all traffic, whether it's encrypted, unencrypted, or compressed. And now most traffic is encrypted. Virtually all of it's encrypted these days. So these older solutions that require payload access to do their deduplication and compression um, basically are becoming almost useless in today's environment. And because we don't require payload access, we're able to eliminate, obviously these you have random encryption, decryption delays at network endpoints that contribute to jitter because, you can have different payload sizes and it can take varying amounts of time to encrypt and decrypt. And that's a huge factor, as I mentioned a moment ago, because most network traffic is encrypted now. And the other side benefit of this is the maintenance overhead and security risk of exposing encryption keys to these legacy vendor tools at network endpoints essentially goes away. And the fact of the matter is, you don't even have control over both network endpoints in most cases. That's really seldom the case now.
hmm.
And it also works with existing network and cloud infrastructure. So if you have SD-WANs and application delivery controllers in place, that's fine. There's no rip and replace required with this.
So Warp VM isn't doing any deduplication or compression, or is it?
No, it isn't at all. And that's the reason we don't require the payload access. And that's
I
huge. And
see.
it delivers the benefits I just mentioned there on this slide. And that's a big contrast between us and a lot of the traditional network optimization solutions that basically work by trying to accelerate traffic by reducing its volume, by compressing it, deduplicating the data, and so forth. But those
Impressive.
techniques usually require access to both ends of the network. Those are dual-ended solutions. Warp VM and all of our solutions are single-ended. They only have to be deployed at one location on the network. So how does this all shake out in terms of dollars and cents? So this is a customer example. So this is a customer example based on AWS. And so this is meant to walk you through what traditionally happens if somebody wants to do an upgrade. And let's assume that you've got a customer that's currently paying for 10 gig port capacity, and they want to improve throughput by what we see on average with Warp VM, which is about 3x. What they would do to achieve that is they typically pay AWS for 2 additional 10 gig ports and balance load across each at about 30% utilization. And they're doing this to allow headroom for peak traffic. And as we discussed earlier, that leaves resources underutilized, and you're wasting money most of the time on those underused resources. Now, based on AWS Direct Connect pricing, the additional cost would be $32.85 a month because AWS charges $1642.50, just as it says on the slide, for 10 gig port capacity. And you can verify that yourself. What you see on the left-hand side is a screenshot from the AWS site. And anybody in the audience can go to that link and try it for their own implementations to see what it would cost them to do the standard AWS approach. But the thing is, this doesn't include the cost of 2 more AWS machines that meet whatever your requirements are for CPU, memory, and so forth. So the real costs are much greater than this additional $32.85 a month. Because remember, when you provision for peak traffic, and the way I described it is pretty typical with what we see at most customers before they implement us, is that they do this kind of load balancing. They're utilizing about 30% of each port's capacity and so forth, and implementing basically, in this case, 3 VMs to balance the load across corresponding to the 3 10 gig ports. They're only using about 30% of them most of the time. Now, to improve throughput by Warp VM's 3x average, in contrast to what you do with the standard AWS approach, and an AWS customer can certainly use us instead of in the AWS cloud, instead of going the traditional route. remember, we deploy as a virtual network function in any cloud environment.
Mhm.
The customer would only pay us $883 a month, and that's at list. So that's about 73% less than the traditional AWS approach that we've been discussing. And again, the savings are actually much greater than 73% because AWS machine costs can be huge. And you don't have to implement any additional AWS machines when you're using Warp VM because this need for allowing headroom for peak traffic goes away because we've addressed this critical problem of jitter-induced throughput collapse that causes a lot of this over allocation of resources.
Okay, so you're saying Warp VM eliminates that provisioning for peak load. That's the big area of wasted cloud spending when we talked about at the beginning in our title of the antidote to over provisioning.
Yeah, it is a big component of it. And the other thing that drives these continuous upgrades is the fact that, just adding bandwidth, it only works for a time because you haven't really addressed the jitter response of TCP. And so consequently, your traffic goes up to the new capacity that you've added in a short amount of time, and you're back to the same place. Performance starts lagging, and you end up going through another round of upgrades that become increasingly expensive every time you do it. And that whole process goes away with Warp VM. So not only do you save money on the initial upgrade, you save money over time because you're not constantly having to upgrade to deal with the fact that now performance is poor again. That problem really goes away with Warp VM. Now, if you're a cloud vendor, Warp VM obviously benefits you too. It can drive massive operational efficiencies because you no longer have to incur the cost of provisioning additional network and server infrastructure to deliver the equivalent of a 3x upgrade that we've been talking about here. So, obviously you can do a lot more with your existing infrastructure just as your customers can. So there's benefit for you too as well. And obviously the cloud vendor can decide to pass some of the savings on to their customers or pocket it, whatever they decide to do. But there's obviously massive operational efficiencies for the vendors as well.
And those vendors could also support more customers and generate more revenue from their existing infrastructure.
Exactly.
Brilliant.
Exactly. Okay, so this is proven technology, and this is just a sampling of some of our major customers and partners, and these are all recognized names. I think everybody in the audience knows most of these organizations, and they've been seeing the kind of benefits that I've been talking about during our time today. So this is proven technology. It's been out there for years. Really, you're not taking any risks with this. And in fact, if you don't deploy it, you're missing out on quite significant savings, as we've been discussing.
Since it's clearly proven technology, how can a potential customer partner get this in their network? Do you offer a free trial of some kind?
Absolutely, you can request a free trial. Okay. So we offer 15-day free trials. You can go to the Warp VM product page, the link you see there, on our website. You can get more technical information about the product, get the tech specs for it. And if you scroll to the bottom of the page, there's a push button that'll take you to a free trial request form. Or if you prefer, you can email us at sales@badunetworks.com, request your free trial, and ask any questions you might have about the product that way as well. So yes, fully supported 15-day free trials available. And it's definitely worth the time and energy put into it. And in fact, Warp VM, because of the nature of it, deploys pretty quickly. So it's really not a heavy lift to try this software out in your cloud environment.
Fantastic. Well, thanks so much for giving us an overview of this innovative approach. It really is intriguing. And I look forward to hearing more as you continually innovate and deploy on new networks with new customers. And congratulations on the tremendous success you've been having.
Thanks a lot, Evan. I appreciate the time today.
And thanks, everyone, for watching. Appreciate your time. And keep in touch with us here on social media, Twitter, LinkedIn. Happy to address any questions you might have. Take care, everyone.